Okay, welcome back everybody from our Labor Day holiday. That one's always weird because it happens within like a week of the first day of class. Although I feel like during the pandemic, everybody could use as many vacation days as we could possibly get. So hopefully you guys got some time to relax. Let's take a look at some new problems. So we'll move on from phase diagrams to horizontal. Yeah, thank you. We'll move on from phase diagrams. Well, let's see. So we did heat curves. We did phase diagrams. And all these things are kind of tied in together. But let's move on into a somewhat new topic, and we'll look at we'll start looking at colligative properties. I guess before we get into colligative properties, we can talk a little bit about solutions, because those two are kind of interrelated. So solutions, let's see, what's the key things here? I guess the other thing is, let me look at my problem set here. Yeah, we should probably recap on intermolecular forces a little bit too. Let's start with intermolecular forces because I think that follows a little bit more naturally from phase diagrams. And then we'll take a look at what happens when we take a solvent, like a liquid water or something like that, and we dissolve some sort of solute in it, like salt or sugar or something. What happens with the potential energy for that, and what the consequences of that are, for our phase diagrams and for all these other kind of things that we look at, boiling point, etc. Well, boiling point is part of the phase diagram, but for osmotic pressure, I guess, isn't represented on there very well. Okay, so we teach about intermolecular forces. If you took 301 at UT, you should have learned about these already. They're kind of tough, I think, especially in general chemistry. They're kind of difficult, I think, for students to get because we spend such a brief amount of time on them. When you get into other chemistry courses, if you go on to take organic chemistry or inorganic chemistry or something, you get sort of a better idea of the structure of what things look like. And I think things like intermolecular forces are a little easier to wrap your head around. But right now, as introductory students, there's not like a lot of chemicals that you know. It's not like you can conjure up an image of like acetone or octane or something. Like those don't necessarily mean anything to you. You know what some ionic compounds and stuff are, but that's not particularly useful for this. So, but intermolecular forces, so these are the weak forces that, we'd call them like non-covalent bonds. And so like covalent bonds, remember, is like if I have like what you think of traditionally as a bond. So if I've got like a carbon-carbon bond, so this is ethane, these things that we usually represent with a solid line, and we talk about having 2 electrons and we draw Lewis dot structures for, that's a covalent bond. That's usually what we're talking about when we're talking about bonding in chemistry. But the other thing that we talk about that's actually probably more important, and especially now, like in modern chemistry, I think it's becoming more important because it has so many applications in biochemistry, are non-covalent bonds. And these are these weak intermolecular forces. So, we've got things like water, where you can have hydrogen bonding. So hydrogen bonding. And hydrogen bonding is probably one of the more complicated intermolecular forces. But we also have some other ones like dipole moment. So if you have, what's a good example of one with a dipole? Let's say you have some compound like this. So fluoromethane. So I have a carbon and I've got a fluorine attached to it. there's going to be a dipole there. And so if I have like a pure liquid of this, the dipoles will tend to align such that they oppose one another. So let me put this in a different color. So this one also has the same dipole, right? And they're going to lie in opposite directions. And so the dipoles on those two molecules will align with one another. Another way you'll sometimes see this written is we'll use these little tiny lowercase Greek letters. So that's a delta. You'll say, okay, that's got delta positive and that's got delta minus. And so when I have it interacting with another solvent molecule, I'm going to expect those to line up. In the exact way that you would think, which is just that, opposite charges attract one another. So this is what a dipole looks like. And then we have this other one. I'll get back to hydrogen bonding in a second. And then we have the weakest force, which is, in any molecule that's in a liquid state will have these forces, but we have these what are called dispersion forces or van der Waals forces. So if you have something like, I'll just stick with this theme of small organic molecules. If I have something like ethane, this bond isn't polarized at all because it's carbon and carbon. So if the atoms are identical, then you have something that's just purely covalent. There is no actual set dipole there because the atoms have the same electronegativity. That's how I'm drawing up here in this area. I know where the positive and the negative goes based on the electronegativity. So if you're weak on this, that's what I'm working on. You might want to go back and just take a look at the GChem website on that. Down here, I don't have any kind of dipole. And so how do these things stay together in liquid form? Like, what's holding them together? What are the non-covalent forces that keep them attracted? And it's what ends up happening is you get temporary dipoles. So let's say that you're in a flask or something and this ethane is a gas at normal pressure, but like say you have a pressurized gas line or something, like you're transporting natural gas in a pressurized gas line, so it's a liquid. What's holding it together as a liquid is like one of these molecules might bump into the side of the pipe and pick up a little bit of charge. Let's say the pipe has a little bit of negative charge on the side. That means that this will then become positive because the electrons will be repelled from it, and you'll get these temporary dipoles. And this will propagate throughout the solution, so this negative charge will then repel the electrons on the other one. And so you sort of have this like flux of temporary dipoles that are happening. Sorry, let me check to make sure I'm hit record. Good, I did. So you have this sort of flux of dipoles that are happening there, and they're very weak, which is why ethane is not a liquid at room temperature and atmospheric pressure, because there's just not enough, enthalpy, I guess you could say. If you think of the bonding in terms of enthalpy, there's not enough enthalpy to hold it together. And so the entropy term kind of takes over and forces it to go into a gas. And so you'll hear these referred to as a bunch of different things. The best, you hear them referred to as van der Waals forces or dispersion forces. I like the term induced dipole because it actually tells you what the hell's going on there. You have induced dipole moments that are just these kind of like temporary dipoles that form from the electron cloud being somewhat polarizable. In hydrogen bonding, we don't really need to get into like how complicated it gets. The explanation in most textbooks is not correct. And most people have some confusion around it. And while I would love to talk about hydrogen bonding in like really great detail, you can think of it as being, it's a very very strong dipole interaction. And the reason it gets its own special name is because it is significantly stronger than a normal dipole-dipole interaction. And this is the part that usually is left out inside of textbooks, is that there is an actual like small covalent component to the bonding. So there's a little bit of a covalent bond that kind of builds up between these two guys that contributes to a bunch of different properties of water. In particular, like if you look at like a normal dipole, now I'm getting deeper into this than I want to get, but if you look at a normal dipole, like how these things line up, they just line up in terms of their charges. So like this carbon and this fluorine, it's kind of like not super directional. Covalent bonds have very like set geometries, which you're aware of, because you know we teach you all that stuff about like sp3 is 109.5 degrees and et cetera, et cetera. And we see some of that when you look at hydrogen bonds. So hydrogen bond kind of has a little bit more like it's able to kind of organize things a little bit more. So water has a little bit more of like a set structure to it. Whereas when you look at these types of things, they tend to just kind of like tumble around each other. Anyway, you don't, well, I'm not going to test you on that, but just so you know, that's the deal with hydrogen bonding. But so we have these different intermolecular forces. Hydrogen bonding can only occur when you have like that's like a small set of things. So it's either like a nitrogen hydrogen, an oxygen hydrogen, or a fluorine. And a hydrogen. So these things can all form hydrogen bonds. They're hydrogen bond donors and acceptors. Everything else is not a hydrogen bond. So even though like this, chlorine and hydrogen, you've got some polarized, this thing is somewhat polarized, it just doesn't form a hydrogen bond. And why is that? You know, it's complicated as I kind of hinted at, but mostly we know because we've looked at it and we've studied it and we just know what hydrogen bonds look like. So these are the only ones that can form hydrogen bonds. Other common mistakes in intermolecular forces, you can see I like these things, I'm talking about them a lot. But other things is that CH bonds are not, let me get back to that question in the chat in a second. CH, this is not polarized. We consider a CH bond not polarized. And, you know, if you look up electronegativities, you'll see that it is kind of polar. Electronegativities are like useful guides. Like it's kind of a useful, like a pragmatic tool for describing polarity. And they have formal definitions around them. But when you actually do like the high level quantum mechanical calculations on the CH bond, you see that it's like not polarized at all, or very, very, very slightly polarized to the point where we just consider that not polarized. So you can think of a CH bond as being purely like kind of a pure covalent bond, and that it's not polarized at all. So, you know, when I went back down here and I drew out ethane, even though it has hydrogen and carbon on it, which are different atoms, so you might expect some polarization there, it doesn't actually contribute much at all. All right, so there's your crash course in intermolecular forces from someone that really likes intermolecular forces. Let's see, might be a dumb question. Does that mean one NOF and a hydrogen need to be in the same molecule? Oh, like if you have a nitrogen on one, and I think I understand the question. That's a good question. I think I understand the question at least. So right now, I guess what I would say is right now we're restricting it to just talking about a pure solvent. So in a pure solvent, yeah, you need to have like, for example, NH3, or if you're looking at, I don't know, what's another one? Like if you, here's one where you at least have something interesting in the molecule happening. All the hydrogen bonding in this takes place right here. So the hydrogen bond acceptor are the electrons on the nitrogen, and the hydrogen bond donor obviously is the hydrogen itself. And so you can get this nice structure. Let me redraw that because it's tetrahedral. So I get this nice structure where I have hydrogen. I can get some hydrogen bonding between these things. So, you know, I've got my hydrogen bond that forms here between the lone pair I did a crappy job of drawing that, but that's supposed to be like a little dash line between the lone pair and the nitrogen and the hydrogen. The question that Daniel is asking is, do they have to be in the same molecule? So you always have to have, in order for something to be a hydrogen bond donor, it has to have this structure. Donors always have that look. So if it's going to donate a hydrogen bond, which when I talk about the donor part, I'm talking strictly about the actual hydrogen. So the positive part always comes from one of these bonds. The acceptor can be a lot of different things. So for example, if you look at acetone, it doesn't have any hydrogen bond donors on it because it doesn't have any of these little motifs that I've drawn over here. It doesn't have a nitrogen, a hydrogen, or anything. But it does have a hydrogen bond acceptor on it. So if you mix up ammonia and acetone, yes, the ammonia itself can hydrogen bond with other ammonia molecules, but you can also have interactions like this. And when you go on to take, this is what I'm talking about now is already going farther than we typically will test you on. But when you go on to take biochemistry, for those of you that do go on to take biochemistry, which is like a pretty cool class, I recommend biochemistry. You'll see that like inside of enzyme pockets and stuff, you get the inside of enzyme pockets and stuff, these types of intermolecular forces and stuff are like really, really important. Enzyme pockets are where, chemical reactions happen inside of the body. So anyway, so yeah, a little bit of a sidetrack there, but yeah, you can have intermolecular forces is a pretty deep, you're welcome, is a pretty deep hole. Like I could spend a month or a whole semester. There's a whole field dedicated to it. So, whatever, you could spend a lifetime thinking about it. Can we quickly go over how IMF strength between C5H12 and CH4 compare? Sure. C5H12, yeah. So, if you're looking at a big long molecule like this, so this is C5H12, versus another molecule like CH4, which I don't need, I can't even write an abbreviated formula for that. Which of these are we going to expect to have stronger IMFs? So they have the same IMFs. They both have dispersion forces. So what does that tell us, though? But I guess, well, it doesn't tell us anything. What's unique about this, or what's sort of interesting about this, the question is that for this C5H12, which is pentane, this is a liquid at room temperature and atmospheric pressure, or whatever. Just always assume we're at atmospheric pressure unless I'm saying otherwise. Whereas this is a gas at room temperature. And you know that methane is part of natural gas or whatever. And so, like, why is that? And it's just that dispersion forces are weak, but as your molecule gets bigger, you just have more sort of surface area for you to interact with the other molecule at. So I can take a pentane molecule and stack it. I'm going to abbreviate pentane. I don't want to do that. It's going to look confusing. But, if I take another pentane molecule, like, I guess what I'm saying is intermolecular forces are additive. So I can take another pentane molecule, let's say, and when those two stack, I've got I've got all the, that's not what I wanted to do. I've got I've just got a lot more surface area. So each one of these could potentially have little dipoles on it. So like, let's say I have a positive here, that means I'm going to have a negative down here. a negative there, a positive there, a positive here, a negative there. So I just have like a whole bunch more intermolecular forces just because the molecule itself is bigger. So I have more interactions for the dispersion forces. Whereas in methane, I mean, for one thing, it doesn't even have another carbon atom in it, so it's smaller. This is the smaller it is, the less able it is. You wouldn't know this, but like the smaller the electron cloud is, the less able it is, I guess you could say, to be able to kind of have these induced dipole moments. But you only ever have the interaction. You only ever have the chance. Let me draw these consistent with one another. You only ever have the chance for like one dipole interaction there. So like this one might be positively charged, and then this one might be negatively charged. So I only have the interaction between one carbon atom on this and one carbon atom on that. And so, yeah, so it just works out sort of almost intuitively once you think about it, that having more charges or more points of contact, like we have up here, you know, I've got, there we go. So just having more points of contact, you know, I have 1, 2, 3, 4 carbons, 5 carbons if I line it up properly, versus just one, you know, you get more, there's more energy. So each one of those interactions has a certain enthalpy associated with it. So here I have like 4 intermolecular force bonds or whatever. So there's an enthalpy associated with the 4, and that is going to be, you know, approximately 4 times as much as I get from just having those. So they're additive in general. And the same thing is true with dipoles. If we're comparing 2 dipoles, the one with the larger dipole it's more likely to be a liquid at room temperature. So how does this all tie back in then to how does it? So you know, you don't need to know this in like hyper depth. You need to be able to identify the different types of intermolecular forces and then be able to compare which are stronger. So I think we have some problems in the practice that kind of hint at what we look for in exams. But if you're looking at, I guess one thing that we talk about is like stronger IMFs mean like higher boiling points. Higher boiling points, which is another way of saying they have lower vapor pressures. And so if you're comparing 2 different molecules, like for example, let's say you have liquid ammonia that looks like this, and I'm comparing that to something that looks very similar, like methane, and I say, well, which one of these do I expect to have a higher boiling point? This one has, you can list out the intermolecular forces. You're only really worried about the ones that are different. But this one has hydrogen bonding, which is like the, you know, penultimate intermolecular force, whereas this one only has induced dipole. And so I'm going to expect the vapor pressure for this one, let's say the boiling point, that's easier to think about, the higher boiling point, which also means a lower vapor pressure. At a microscopic scale, you're welcome. At a microscopic scale, you know, you can kind of think about why that is, and it's just that it's harder for these things to, you have to, in order for, if you've got a solution, you know, if we're looking at sort of the bulk, these kind of emergent properties from these things, in order for a solvent molecule to eject out of the surface of the solvent, it has to break its intermolecular force. So if that's true, that in order for a solvent molecule to go from the liquid phase to the gas phase, it has to break its intermolecular force, it stands to reason that the stronger the intermolecular force is, the harder it is going to be, or the more energy it's going to take to get it into the vapor phase. And that's why the boiling point or the vapor pressure, where you kind of see these correlations between the two. Let's see, is there anything else to talk about there? I think we got pretty damn deep into this. So, but yeah, this whole field of stuff is really interesting. General chemistry, most of the chemistry classes you take, even if you were to go on and do graduate school for chemistry, the speed at which you have to learn things is so fast that it can take a lot of the joy of learning these things out. Eventually, you'll graduate and have a career where you can kind of just sit with stuff and take some joy in learning again. But yeah, this stuff's really interesting. If you like chemistry, it's pretty fun to get into. And you'll get into it in biochemistry. That's where it's really high stakes, right? Biochemistry is high stakes because that's how we design drugs and stuff. Okay, so yeah, so vapor pressure and boiling point are dependent on intermolecular forces. I'm trying to think about freezing point. Freezing point is probably also dependent on. Freezing point is also dependent on the intermolecular forces. Yeah, it's probably freezing point might be a little bit, in like melting points and stuff like that. I think get a little bit trickier because in the solid state you have like things have to stack in a really orderly way, and so I don't think those correlate perfectly. But the boiling point vapor pressure ones, those we expect you to know. So because no, I'm not going to get off on it. I'm not going to get off on a tangent, but yeah, you can kind of think about that. Like in the solid phase, in the liquid phase or the gas phase, things can kind of move around really easily. But in the solid phase, you have this entropic component. So if you've got like a really big molecule that's complicated, that can become kind of a big deal. And just looking at the intermolecular forces isn't enough. I know water hydrogen bonds are constantly breaking and reforming. That is correct. Part of why it has a high specific heat. The breaking and reforming of the hydrogen bonds specific for water, does that happen for all hydrogen bonds? That's a good question, Reagan. Yeah, so all of these, so covalent bonds, these traditional bonds, like this, these bonds are not breaking and forming. I mean, if you want it on like a deep quantum mechanical level, maybe they are, but like generally you can think of those as being set. They're not fleeting. These are permanent parts of that molecule. They don't easily break. But for intermolecular forces, they're always constantly forming and breaking, at least in a liquid. Let me think about it in a solid. Even in a solid, it probably gets more complicated. But yeah, in a liquid, like in water, for example, hydrogen bonds are breaking and forming constantly. In another solution, like if you have like acetone, which is nail polish remover, yeah, the dipole moments and stuff in here, like those are constantly forming and breaking as well. If you would want to, it's a little bit different from hydrogen bonds. But yeah, they're not set. That's what allows them to kind of be liquid. Is that like you can imagine that in order for a liquid to flow, the intermolecular forces have to be breaking and reforming. Otherwise, they would be kind of just set and they would be solid. In a solid, the bonds aren't as fluid, so they kind of stay and the atoms just kind of vibrate in the solid. But in a liquid, they're constantly breaking and reforming, and that's what gives it that's what gives liquids their properties and allows them to flow. So you can imagine if you were able to like freeze. I guess in really what you're doing, like when you freeze something, is you're taking those intermolecular forces and you're making them static. You're taking them from being these kind of fleeting things that can change up really fast, and you're just making them static. And now you've got that. That's essentially what you have when you have a solid. They're no longer able to break and form as easily. Okay. Yeah, so let's move on to, let's see, let's move on to solutions and think about those. So we have these colligative properties. And these are properties that depend on, or I guess you could say they describe what happens when you take a pure solvent and dissolve something in it that's not volatile. So not volatile things are obviously solids, or like liquids that are just don't have that don't that have extremely high boiling points. So let's start with the solid situation. So this is it's not very obvious, I guess. But if you take a glass of pure water versus like, I'm just going to make a, like, let's say this is like 0.1 molar. Let's keep it simple so we don't have to worry about the Van Hoff thing. Let's say this is 0.1 molar glucose. We can think about, and this is not usually how we think about free energy, because usually you're thinking about an actual process. But if you're comparing the free energies of these, which you can kind of think about, like, which has the lower free energy? And the answer to this question, which is not super obvious, at least not to me. I don't know, I still find myself kind of ruminating is not the right word, but like thinking about this stuff sometimes is, but the answer is that the solution always have lower free energy than the pure solvent. So anytime I have something that's dissolved up in a liquid, it necessarily has a lower free energy than the pure solvent. And there's undoubtedly a microscopic explanation for why this is, involving entropy. And I think the distribution of the kinetic energy or something. But for us, I think it's okay to just kind of accept this as axiomatic and not think about it microscopically. So solutions always have a lower free energy than the pure solvent. What this results in, though, is if you think about, so lower free energy is another way of saying it's like more stable. So another way, so more stable, that's the same thing as saying lower free energy. Sorry for my shitty handwriting right there. All right, but so more stable is an easier way to think about this. And when we're talking about more stable here, you can think about it in terms of phase transitions. You know, if it's more stable, that means that it's going to be harder to boil. And so you can kind of think of like you can think about it as like I've stabilized the liquid state of whatever substance I'm looking at. So I took pure water, like pure liquid water, and I dissolved some stuff in it. And by doing that, I stabilized the liquid state of the pure water, or by turning it into a solution, by making it no longer pure water. And that is a way to kind of think about what happens with the boiling point. So if I stabilize the liquid by making it a solution, now what do I expect to happen? Well, if it's more stable, that means it's going to take more energy to bring it to a boil, because it's, you know, it's more stable, so it's more difficult to get into the gas phase. So that's why I see boiling point elevation. And if it's more stable as a liquid, I'm going to see the opposite when I look at the freezing point, which is that it's going to be harder to make it a solid because, again, it's more stable. So I see freezing point depression. So way to think about that is it takes, because of this stabilization, because the free energy is lower, it takes more energy to make it a gas. And it also takes, or you have to put, I guess I would say you have to put more energy into the system to make it a gas. and I have to take more energy out of the system in order to make it a solid. And we could draw a fancy diagram for that or something, but I think that just saying it verbally probably is the clearest way to do it. Where we want to lower free energy for the phase train, like change in delta G should be a negative for a reaction to be spontaneous. Yeah. Yeah, so if I'm not sure exactly how to answer that question, Eva. Like, things are spontaneous when it's negative. That's correct. Here we're talking about. It's hard because usually when I can see where the confusion is coming in. So usually when we talk about free energy, we're talking about delta G. And here I'm talking not about delta G. I'm talking about just G. So I'm saying that like G of pure water. I'll just put a little P down here for that. And I'm comparing that to G solution. And I'm saying that G solution is less than whatever the pure solvent is. Delta G, if something's going to happen, like if something's going to be spontaneous, must be negative. And usually when we talk about these types of state things, we talk about, yeah, good. Usually when we talk about these types of variables, like state variables, we almost exclusively talk about them in terms of delta G. And there's a lot of reasons for that. But yeah, so we're talking about boiling point elevation and freezing point depression. So if you want to think about it in terms of delta G, let's say that you have G and it's increasing here. I'm trying to think of what would be on the x-axis down here. But if I'm starting, what's a way to say that? No, I don't want to get into that. My PChem's not good enough. I'm worried I'm going to dig myself in a hole. One way to think about it is like if you, it's kind of like if you're looking like, if you're thinking about lifting a weight up, like let's say I have a, that's not what a weight looks like. All right, let's say I have like a 100-pound plate. So I have a 100-pound plate. That's a really big plate, actually. But anyway, I'm trying to lift that up. I should have given myself more space here. If we think about it again, something that we're used to talking about, like gravity, where you're working against it. If I have to lift that plate up, let's say to some height here, it's like, let's say I'm trying to get it 10 feet off the ground. And here I'm starting at ground level. You know, it's going to take me a certain amount of energy to get it up from here. It's going to take a certain amount of work to get it from here up to here. So, you know, I put in some work and I raise it up to the 10 feet. I'm at the gym and I picked up 100 pounds. I don't know, 10 feet is pretty goddamn tall. This isn't a very realistic example. Let's say that you're 9.5 feet tall. So this is reasonable and you can lift that up over your head, whatever. All right. What I've done, so like this, in this instance, this is like the pure water. When I dissolve a solid into the pure water, what I'm doing is, it's like I'm still having to go up, and this isn't an exact analogy, but you know, I'm still having to lift it up to 10 feet. But now, this is the ground level. What I've done, it's like I've lowered the potential energy of it. And so now I'm like lower than ground level. You know, it's like, let's say I'm like, you know, if I'm like a couple of feet below, now when I have to lift it up, I'm lifting it up to the same spot, but I'm not actually getting up 10 feet, right? I'm having to go this additional bit here. So I'm still 10 feet off of the ground, what I'm calling the ground level, but I had to lift it some additional amount. And so it just takes more work to get it up. So this semi-elaborate example here, all I'm saying is that, you know, if you compare it to like lifting a weight or something against gravity, the lower something is, the more work you're going to have to do to kind of lift it up. So if I'm picking up like a textbook, this is probably a smarter example. If I'm picking up a textbook off of my desk and I'm putting it up on a bookshelf, that requires a certain amount of energy. If I put that book on the floor though, and I pick it up off the floor to put it up on the shelf, that's going to require more energy to do that because, you know, it's lower. So so I've changed its potential energy. I've lowered its potential energy. So I'm going to have to work harder to kind of get it up to the shelf. That's essentially what's happening with a solution. It's like you have the pure water, right, which is like my book is on the desk, and it takes a certain amount of energy to bring it to the boiling point, which would be 100 degrees Celsius. When I dissolve a solid into that water, it's like now I've taken that book and I put it on the ground. I still need to get it up. This is where the analogy kind of falls apart, but I still need to bring the potential energy up to where I can get it to boil, but it's just a larger distance that I have to get it up. And we kind of see that shake out in terms of the boiling point elevation. So the actual temperature you have to get it to is higher. So you guys are having your own. I am 9 feet tall. God damn. Okay, lots of good questions here. Yeah, so you're asking about the microscopic explanation of why is the free energy lower in aqueous solutions than pure water? It's definitely an entropic term, as somebody else I think points out. I think what's happening there microscopically, one way to think about it is, the explanation is it's not like super complicated, but I just didn't want to get super deep into it. But you're changing the, even though you're at the same temperature, like you're changing the, I'm trying to think of a really good way to explain it. So some of the things that you're dissolving in there are big, and so it takes a lot of kinetic energy to move them around. So if you imagine that you have, I was hoping to do some of these problem solving things, but this is way more fun to talk about, so I'm fine with that. But if you think about pure water and we just represent it as like, wait, sorry, now I'm trying to think of what the question was. The question was, why does it lower the free energy, not why does it lower the vapor pressure? Let's see. I think the answer is that your kinetic energy distribution is broader if you have a dissolved solid in there. But generally, not getting into something super deep like that, you can just think of it as being an entropic term, right? If I dissolve a solid in there, I'm giving more, there's more available different like little microstates or whatever that the solution can be in. So like you're in, I hate explaining it. It's just such a bad way to explain things. But you think about it, you're increasing the disorder of the pure liquid. So pure liquid, it's like there's only a certain number of ways that you can arrange it. If I dissolve salt in there, now I have more ways that I can arrange it. And so I've increased the entropy of that system. And so in that regard, I've lowered the free energy. So that's a way to think about it. I don't find that explanation extremely satisfying, but the solution. Higher entropy equals lower free energy equals more stable. Yes, that is a perfect explanation. Yeah. Yeah, don't let me go off on this like Boltzmann distribution thing. All right. So yeah, so those were intermolecular forces. That was more of a review of intermolecular forces with some other stuff sprinkled in. Oh, I know what I wanted to get to. Last thing to think about. this is again something that's like not super intuitive. And if you want to think about free energy and entropy and stuff, this is a really great kind of thought experiment you can do, which is if I take a beaker, of pure water, I'll leave some space here. Let's say I have some pure water here. And then over here, I have salt, like a solution of glucose. It doesn't matter what it is, you know, 0.1 molar, 1 molar, whatever. It looks like it says glucose. Let's just call it sugar. Sugar solution. We know that the free energy is lower here. So, yeah, I'm not going to write that out. But if I take this and let's say I enclose this now, so I put like a, you know, like a cake dome kind of thing over it. And I put those together. So now they can't exchange water out with the atmosphere, right? There's no, the system's kind of sealed off from the environment. If you just let that sit for a long time, what will happen, I don't know if you predict this. I think I posted some new lectures last night. It's possible I didn't make them public. I'll go double check that when I upload today's problem solving thing. Yeah, what you'll end up with, this is a fun, you can think about this, is that all of the water will spontaneously transfer over here. So this one will be empty. And it's still closed in. This one will be empty. And your sugar solution will just get diluted. So I leave you with this thought experiment of like, why does this happen? And you know, if you're like drowning in like work right now, like you're like can't get through stuff, don't kill yourself trying to figure out exactly why this happens. Like there's a lot to think about here, and you know how if we ask you a question on a test like this, it would be pretty basic, but this is in terms of things to kind of wrap your head around and trying to understand delta G and delta H and delta S and stuff. This is kind of a cool experiment. Yeah, so people are already kind of talking about it in the chat window, and I encourage you to talk about it because it's kind of fun to talk about. This conceptual stuff is like, oh, this is where it's at. So in terms of lectures and stuff, so with the next part that we're getting into, I know you guys have to get to your next class, but the next thing that we're going to get into is equilibria, like not equilibria like we talked about with phase transitions, but like equilibria, like chemical equilibria. And so if you took in high school, I feel like we get into it a little bit where you're talking about equilibrium constants, you know, this equilibrium constant K and stuff. This stuff that we're getting into with equilibrium is one, it can be problematic for students. A lot of people struggle with it, and there's reasons for that. It is kind of complicated, mostly because you have no experience working in a chemistry lab, so you have nothing to attach this stuff to. But the other thing the other reason I bring it up is not just that it's kind of difficult, but also because it will be in everything for the rest of the semester. So it, you know, like anything, or chemistry, like more so than other subjects, builds. So get the chemical equilibria down as best as you can and put a lot of work in now, and it'll make the next section easier and the next section after that easier still. It's somewhat, it's not like math intensive per se, but it does use algebra, and you have to connect the algebra into, I think this is where people get lost. You have to take the algebra and you have to connect it into this chemical intuition. And that can be really challenging for students. So I'm just emphasizing it because like if you get lost now and you get kind of swallowed up with other work and you don't get to it, then our next exam is just like all chemical equilibria. And then the exam after that is on acid-base chemistry, which builds on chemical equilibria. It's just like a more complicated version of chemical equilibria. So your life is basically just chemical equilibria for now until the end of the semester. We get through electrochemistry, it changes a little bit. We still see a little bit of equilibrium expressions, but the next two exams are, exam 2 and exam 3 are like equilibrium to the max. So just be mindful of that as you try and balance your time and think about like what you want to get deep into. I think the nice thing about the equilibria stuff is you can kind of work it methodically and sort of build, if you do enough problems, you can just kind of solve them even if you have no idea what the hell you're doing. What lectures should we have watched by next time? Well, I guess I was hoping to get into chemical equilibria and thermo on Friday. And I think I'll still probably push for that. I would like to work out at least one problem from, freezing point depression or something where you have to put some numbers in and solve, just so you've seen that and you know what to expect. But yeah, the lectures that I would watch, I forget which ones I posted, but try to start getting into the equilibrium constant stuff. Yeah, try to watch the lectures on equilibrium constant. Yeah, I don't know. I want to dog on my own lectures, but they're not super exciting. But get a feel for them. At least read the GChem website on like mass action and stuff. And then I will try my best, because I really like to talk about things conceptually. I will try my best to move through any kind of conceptual stuff extremely fast on the equilibria stuff, so that we can really get into the problem solving. Because I think in terms of just like, getting a grade and moving on with your life, and just kind of building, I guess it's more like building a foundation for the rest of the semester. Solving the problems is probably the most important thing. So yeah, so get some familiarity. If you can, I would say if you can, like as a starting point, is like understand how to write expressions for K. So if I've got a reaction that's like A plus B and it's going between C, it looks like this. Understand how to get from there to here. Yeah. And then like, that's probably pretty good. Yeah. Get there. Yeah, I guess get there, and then like maybe try and consider like what happens. Like if K is like this, I think I talk about this in the video, versus this, like what does that tell us about this equation? If you can get there before next lecture, you'll be solid when we start solving problems. So brush up on that on the GChem website and stuff. And yeah, watch some of the lecture videos and let me know if there's issues on Piazza, and the TA will let me know and I can improve on it. But yeah, get this stuff down, work hard on the K stuff. Like if you have to like trash some of the material, like don't, like osmotic pressure and stuff, it's like, yeah, that's going to be on this exam and then we'll never talk about it again. The equilibria stuff we will talk about for the rest of the semester. So make sure we get that down. Yeah, all right, let me take a break. I don't know how people sing all day. I must like take like some sort of lessons or something how to speak. My like throat has been like, it's like burning after an hour of talking. I feel like usually during class when it's in person, there's more like dialogue and it's just the flow is different. I don't have to talk as much. But let me take a break and drink some water and stuff, and then I will see you guys in just like a few minutes for office hours, and we can talk about whatever you want. But yeah, drink water. That I don't have vocal. Yeah, vocal fry. Thank you, Chandler. Yeah, I think I do a bad job of like not pushing air like up from my diaphragm. Like I'm a lazy speaker. Anyway, I don't have COVID. That's not what the burning is. I know because one of my friends runs a test lab, and I get tested regularly. Anyway, all right. I'll see you guys in like 2 minutes. Bye, y'all. Okay. Let's see. I still got a bunch of people in here. Yeah, so welcome to office hours. I'm just going to leave these as one continuous video lecture so that I don't have to double post. Yeah, so now we're starting on office hours. Yeah, what do we want to do in office hours today? Kind of got off track. I had like this bunch of problems I wanted to work today during my 9 a.m. lecture, and I just got distracted. I don't know if distracted is the right word, but just, went off topic and wanted to talk about something else. So we have let's see, we have a bunch of stuff here, right? We can talk about heat curves in more detail, although at this point, I think it's, unless you have specific questions about that, probably what you need to do is just sit down and just start working problems on those. So if you haven't gotten there, I would just put that on hold in your brain until you have a chance to sit down and just try and work through every single problem. That's really what you want to do, is just work through every single problem. And then we have colligative properties, which we can talk about. And then we could also dip our toes into, which are not on this worksheet that I'm looking at, but we could dip our toes into looking at Equilibria and stuff. Although I'm going to talk about that in class on Friday, and it's in the lecture videos and stuff. So it's kind of up to you guys, or I can just talk about whatever. Do you guys have any specific interest here?
I had a question about like one of the ones on the problem set.
Good. Okay. Not good that you have a question or an issue, but good that we have something to talk about as a starting point. Yeah. Which problem?
Number 27 and 28, I was wondering about.
27, 28. If I'm looking at the right one. So 27 is about colligative properties for glucose, and 28 is about, I don't know, I guess, what properties affect colligative properties. It's kind of a weirdly phrased question. Is that right?
Yes.
Okay. Okay, so there's two problems here. Let's look at the first one. Okay, so this one is saying, thank you, Madison, for asking. Madison, is that right? I've lost track of your name. I'm sorry, but thank you, whoever asked the question. Okay,
yeah,
good.
Right.
Colligative effects of a 2-molar aqueous glucose solution. So we're looking at problem 27. I'm saying this for the video, but we're looking at problem 27 in the unit 1 problem set. I'm just rewriting it. It's a 2-molar solution. Aqueous glucose solution would be 1 molar. Yeah, this is a good question. I don't know about the wording. I feel like the wording's okay. Aqueous solution. With the same volume. So it's a fill in the blank, a fill in the blank, and it just gets at the like this fundamental thing that we talk about for colligative properties, which is true at least for dilute solutions, or just for any solution we talk about, I guess. It's saying if I've got 2 molar, so the first thing to recognize for problem 27 is that colligative properties, this is the first thing that occurs to me when I read it. Colligative properties don't depend on the nature of the solute. They only depend on the total number of dissolved, I hate to say the total number of dissolved, let's just call them dissolved particles. Particles, maybe like dissolved moles. I don't know. It'll be clear once I kind of show you what I mean. So, but the important thing is that, like, the fact that this is glucose and the fact that this is potassium sulfate, we spent a lot of time in our normal class today talking about intermolecular forces. We don't have to worry about those for colligative effects. Colligative effects are independent of the intermolecular forces, at least approximately enough that we can do some calculations with it. So another way of saying that is if I take, let's look at some examples where things are identical. So the thing that they're trying to get you to work out here is the Van Hoff factor. If I have like glucose, let's say 1 molar glucose, or let's say I have a different solution that's a different sugar, so 1 molar like fructose. These are both sugars with different molecular formulas, or like 1 molar, let's see, what's something water soluble that's not, let's say 1 molar ethylene glycol. So all of these things are, I think we call them in GChem as like molecular compounds. Probably a better way to define them is like they're not ionic. Ionic compounds are when things get weird. So for molecular compounds, 1 molar glucose versus 1 molar fructose, 1 molar ethylene glycol. Even though you don't know any idea what ethylene glycol looks like, or fructose or glucose, maybe even so for that matter, they all are going to have the same exact effect on the boiling point. What are they actually? Effects. They're just asymptotically. These are all have the same effect on the boiling point and the freezing point and many of the other colligative properties that we've talked about, osmotic pressure, etc. And what do we call it? The Van Hoff factor, this guy. I forget how to spell his name. There's an apostrophe maybe in there somewhere, I don't know. But the Van Hoff factor is 1. For molecular compounds. So if you look at one of these equations, like if you look at one of these equations, like delta T equals I little baby m for mol times K, be it K freezing or K boiling, I is what this Van Hoff factor is. And so I is equal to 1. It doesn't even really matter for molecular compounds. But if you look at something like, let's see what the question asks potassium sulfate. What's one second. Okay, so if we look at glucose, it looks like this. So I've got glucose solid. I put it in a glass of water. Now it's in solution, which I'm indicating with this AQ here. So it's going from a solid, you know, I'm putting it in water. So now it's aqueous or whatever, some volume of water. I start out with 1 mole on this side. I end up with 1 mole over here. That's what this Van Hoff factor is talking about. It's just saying the number of moles that I start out with on the, I don't want to call it the reactive side, but like in the solid is, how does that compare to the number of moles I end up in the products? So if I look at sodium chloride, for example, that starts out as a solid and I have 1 mole of it. But when it goes over onto this side and it gets dissolved, it actually breaks up because it's an ionic compound, and that's what happens with them. And it breaks up into 2 moles. So I start out with 1 mole of sodium chloride, but the sum of the coefficients over here, so I sum these coefficients, it's 2. That's what I ends up equaling. So when I look at is it potassium sulfate, is that what they're talking about? Yeah. So if I look at potassium sulfate, I start with 1 of these. I go to potassium plus and sulfate. I go 2. I end up with 2 potassium cations. So I balance that in 1 sulfate anion in solution. So what's going to be I for this? What just happened there? When I sum up these coefficients, I see that I equals 3. Okay. And so if I want to look at it mathematically, I can say, well, I know from this equation that this Van Hoff factor I acts like a multiplier for the effect on the temperature. So if it's 3 times whatever the molality is of the solution, we don't know what it is here, times like the boiling point or the freezing point, it doesn't matter, let's call it KF, the freezing point, whatever that constant is, right? This number, it sort of amplifies the effect of, it amplifies the effect of what you're dissolving in solution. And this, not mathematically speaking, and just kind of thinking about what colligative properties arise from, if we come back to where we started with this, which is that colligative properties don't depend on the nature of the solute, they only depend on the total number of dissolved particles. I'm going to change this to moles. It only depends on the total number of dissolved moles. Then we see why this matters. So if I have something like glucose, which is this, if I take 1 molar of glucose, I end up with, or like, what's the right way to say this? Let me go back down here. So if I have 1 mole of glucose, and I dissolve it up in 1 liter of water. So I got 1 liter of water. I end up with a 1 molar solution of glucose, which is what you'd expect. If I take 1 mole of potassium sulfate and I dissolve it up in water, same amount, 1 liter. Usually when we're solving problems not based on colligative properties, we would call it a 1 molar solution of potassium sulfate, which is true. It is 1 molar potassium sulfate. But because we know that potassium sulfate breaks up in solution, we know that it's not really 1 molar in terms of the number of total dissolved moles, because I have K plus and SO4. So I have 2 K pluses and 1 SO4. If we remove moles from the situation, maybe it makes it a little easier. But so the real amount of, or sort of like real concentration of total dissolved moles is 3 molar. If we think about it just in terms of like, let's say that you have like the ability to have like one actual molecule. If I take one molecule of C6H12, O6, and I dissolve it in a beaker, I end up with one molecule just hanging out in there. If I take one molecule of, like literally just like I have one of these things, one molecule of potassium sulfate, and I dissolve it up in a beaker, now what I really have after I dissolve it is 2 potassium ions and 1 sulfate anion. So from the perspective of the solution, this one has 3 times the number of dissolved species as this one does, which just has 1. That's what the colligative properties are getting at, or what the question is getting at, what the Van Hoff factor is, in like a really deep answer to kind of what the initial question is, right? So what is it affect on the colligative properties? Colligative factor under 2 molar solutions would be, what are the answer choices for this question? I see, greater than, the same as, or less than. So the colligative properties, I see. So now you've got a 2 molar aqueous glucose. So you got one more step you have to do. It would still be less than, because we said down here that a 1 molar solution of potassium sulfate is really 3 molar, because I have, for the same reason that we looked at with a single molecule, I have 2 molar. I'm 2 molar in potassium and 1 molar in sulfate. That's a good way to look at it. 1 molar in sulfate. So that's 3 molar total in terms of just stuff that's dissolved. What the identity is does not matter. Versus if we change this now, let's say that we have 2 moles, so we actually are doing the question properly. So now I know that I just have 2 molar there. And so since it's only dependent on the total amount of stuff that's dissolved, the potassium sulfate is going to have a bigger effect on the colligative properties. So even though you have 2 molar aqueous glucose, it's still going to have less of an effect on the colligative properties than a 1 molar solution of potassium sulfate. 1 molar solution of potassium sulfate is really a 3 molar solution. It's 2 molar in potassium plus and 1 molar in sulfate. It's just more convenient usually to talk about it in terms of like it's not actually broken up into potassium and sulfate. Does that make sense? It was maybe a longer answer than you wanted for that. Madison, you still with me? Okay, cool. But yeah, so in addition to like this being kind of important for colligative properties, being able to kind of understand the stuff of like potassium sulfate, and it breaks up into potassium plus and sulfate, being able to kind of balance those simple ionic equations that we learned in general chemistry, and maybe you haven't anybody's thought about that in like at least since over the summer, is important. It'll be important for the rest of the course. So make sure you know how to do that. Go back and practice that now while things are a little bit not easy, but easier than they will be later if you don't get it. damn it, so it's less than. The colligative effects of 2 molar aqueous glucose solution would be less than, yes, correct, 1 molar potassium sulfate aqueous solution at the same volume. Yeah. Because 2 molar glucose is 2 molar oil, and the 1 molar potassium sulfate, it's not 6 molar, it's 3 molar. It's 2 molar in potassium plus and 1 molar in sulfate. I know it's confusing to think about, and I don't think we do a great, yeah, okay, cool.
Is there a better way to say it instead of like saying 2 molar overall and like 3 molar overall? Is there a better way to differentiate?
Yeah, it's a good question. I don't deal in colligative. I don't know what the like people talk about it in the literature. 3 molar overall sounds good to me. If you want to be more precise to where it like more accurate in the description, you could say that I like this description. I like the description that a 1 molar solution of, God, it's so confusing even when I'm saying it. Like I understand it because I do this for a living, but like I don't feel like it's super intuitive when I say it out loud. But a 1 molar solution of potassium sulfate is really the same as what you really have when you have a 1 molar solution of potassium sulfate is a 2 molar solution of potassium and a 1 molar solution of sulfate.
Mm-hmm. So you would only call it, sorry, Leo.
Yeah, go ahead.
Oh, you would only call it that like 3 molar overall whenever like it specifically says you're talking about colligative properties?
Yeah, that's a better way to say it. Yeah, like when you're talking about colligative properties is when you care about this.
Okay.
Usually in chemistry, right? Like the identity of the chemical matters because that's the whole subject is based on. Like usually you're like for example, when we go through and we look at solubility properties, sulfate, we actually care that it's 1 molar sulfate, or we might actually care that we have 2 molar potassium plus. But colligative properties are kind of like ignorant to whatever the species is. So like really we're only worried about what the total molarity is for those things, and that ends up being 3 molar. And so yeah, we're using this awkward terminology like, oh, it's 3 molar overall to describe it. I mean, really, like if you really, not that I'm encouraging this, but like, really if you just like remember that to calculate I, you write out the ionic equation and sum up the product sides, the coefficients. You can just always use that to kind of plug in and solve these problems. But I think the way you're kind of thinking about it is better. Does that make sense? So colligative properties are this weird ass case of like, we don't care about it. Honestly, I don't even know why we teach this in chemistry. I don't really, it just belongs in like a physics class or something.
Sorry, I had a question. Are we ever comparing the free energies between solutions, not a solution and its pure solvent?
That's a good question. Like if you had like a 2 molar versus like a 1 molar.
So in this, since like the glucose molecule doesn't like break down into smaller ones compared to the potassium sulfate, in this case, I would assume that the potassium sulfate has a lower free energy.
Yeah, I was just like talking to one of my friends about this. I was getting myself was getting confused on this. So yeah, which would have a lower? I think the more you are getting 3. God damn it! It depends on what you're talking about. I think I guess if you're comparing solution to solution, I would think the more dilute solution is generally going to have a lower free energy. Let me just say this. Let's not worry about it for the exam. I'm not 100% sure on the answer, and I don't want to confuse myself and you, and I'm not going to ask you a question about it. The main thing for you to worry about is like what happens with a pure solvent and a more concentrated. Well, I guess you do have to kind of know about concentrated solutions, liquid for osmotic pressure. Let's see. Yeah, all right, I'm going to make this statement, and I think it's true, which is that the 3 molar solution is going to have a higher free energy. These things get too complicated. So usually when we're talking, the reason I get confused on this is usually when we're talking about free energy, we're talking about delta G. So, if you're talking about, let's say, maybe we can do that thought experiment. Let's see. I guess, yeah, I guess yeah, now that I'm thinking about it more, I'm tending to agree with you that the 3 molar solution would have a lower free energy than the 1 molar solution. Okay. Yeah, let's see. So with that true, so if we set up, let's say we had an experiment where we have a membrane here. So we have 3 molar on one side and 1 molar on the other. What are we going to expect to happen there? Yeah, water molecules are going to flow this way. Okay, yeah, no, we're in agreement. Okay, cool. Yeah, thanks for asking that. Cleared it up in my head. Yeah, so the 3 molar solution. So you do have to know that because we talk about it in terms of osmosis, and the higher concentrations will have lower free energies, which I guess is intuitive since the pure solvent versus the having something dissolved in it. You know, we can see that a pure solvent always has higher free energy than something with that's a solution. It would make sense that the more concentrated the solution is, the lower its free energy is. Yeah, okay. Yeah, no, that makes sense on just like first principles. Okay, excellent question. Yeah, so this one has a lower free energy. Yep, sorry.
If you had a 3 molar glucose and then still the 1 molar potassium sulfate, would they wait?
Sorry, say that again. So 3 molar solution of glucose versus a 1 molar solution of potassium sulfate is the question?
Yeah, so they would both have 3 molar overall, so would they be at the same free energy?
Yeah, I think that's how we think about it. Ignoring, like,
Okay.
yeah, let's just say yes. In terms of colligative, they would have identical colligative properties and approximately the same free energies. So let's just say yes on all of those things.
Okay, so when you're thinking about free energy, you want to think about it in like the colligative way.
Yeah, for this, specifically in this chapter, yeah, that's what we want to think about. And I think it is true too, even on a broader level. And the reason for that, I think the reason that colligative properties work this way is because I think I had mentioned this in one of the videos, is that the enthalpy change for dissolving things is very small. So there's not a huge enthalpy component. And so the entropy component is really dominant. And entropy is like less, entropy has more to do with like statistical distributions of particles and less to do with bonding. I don't know if that actually makes sense. Entropy doesn't really give a shit, I guess, about what the identity of the thing is. You know, like when you look at like gases mixing, I have 2 gases, they're going to mix together. If I have 2 different gases separated by a valve and I turn that valve, the gases are going to mix together because of entropy. But the entropy, whether it's xenon gas and argon gas or hydrogen gas and oxygen, it doesn't matter. The entropy drives it the same way. And I think the same thing is true with colligative properties. I don't know if that makes sense, but the entropy component, I guess a short way to put that is just that the entropy component, if entropy is the driving force, then you can ignore the chemical identity of what's involved in the system. If that makes any sense. I don't know. But anyway, to get back to your answer or your initial question, which is for us, for these solution type things, yes, when we're thinking about the free energy, all we're concerned about is the overall molarity of the solution. Short answer.
Thank you.
Yeah. Sorry. I like, in my mind, the interesting part a lot of it is like, let's dig down and like get to this like really weird microscopic stuff. And sometimes I just get sidetracked just because I enjoy it. I mean, I'm a chemist. I like this subject, right? Anyway, excellent question. We're going through calculations for colligative properties number 21, 29. Oh, I didn't get to 28, which was another question. I can answer that one really quick. And then we can look at these other ones that Madison's asking about again. 28, what solution properties affect its colligative properties? Intermolecular forces. So this is kind of what I'm getting at in the other one. Yeah, for 28, it's like, what affects colligative properties? And the answer is molality. And that's it. Intermolecular forces, molecular weight, polarity, all these different types of things don't really matter. The only thing that affects the colligative properties is the total amount of dissolved stuff. And molality is a measure of concentration, and thus molality is the only one that matters. Yeah. Because like IMFs and stuff, right? That would imply that if it did depend on IMFs, for example, that would imply that like a 1 molar solution of, let's just say potassium versus a 1 molar solution of, let me not use potassium because it's ionic. So you might expect like these would have different properties because they have different intermolecular forces, and we just don't see that. Same thing with molecular weight. We don't see a difference between the boiling point elevation for either of these solutions, so it can't be dependent on molecular weight. And the same is true of polarity, which is really just another way of talking about intermolecular forces. We don't see any difference. So a 1 molar solution of something of one compound, ignoring the Van Hoff issue, is equivalent to a 1 molar solution, at least if they're overall 1 molar, of another compound. So nothing matters except for the concentration. That's the answer to 28. Let's see.
If you had a, I'm not sure if you already said to like not worry about it, but if you have a compound that's like not completely soluble in water, how would you calculate, like if you had like calcium sulfate, right? That's not soluble. Would that,
Let's see. Yeah, I mean, certainly
that,
for
like,
the
change?
exam. Yeah, certainly for our exam, we're not going to look at that. We'll look at, I don't know that we'll ever tie it back into colligative properties, although that's not a bad idea to do that, but we're not going to do that this semester. It matters because it depends on what actually gets dissolved, you know? So if you get, like, let's just, even if you're not thinking of something that's totally, or not, like let's actually, calcium sulfate is a good example. So calcium sulfate is partially soluble in water.
Mhm.
You know, once you get beyond saturation, it doesn't matter how much more you add. You sort of max out at whatever it saturates at. Does that make sense?
Yeah.
Like if I saturate a solution, and let's say that the max, let's just, for making it easy to think about, let's say that the maximum amount of calcium sulfate I can get in this solution is 0.1 molar. So I got 0.1 moles, I put it in a liter. Now I'm saturated, right? And I keep adding. So whatever the substance is, let's say I add it. Let's say it hits the saturation point at 0.1 molar, and then I keep adding it in. It's just going to go to the bottom of that flask, and it's not going to dissolve. So solids at the bottom of the flask. Won't affect colligative properties.
Okay.
Yeah, if they're not dissolved. And like, you know, the way that a complicated question, if not dissolved. So really what we're looking at is like the total dissolved solids inside of a solution when we're talking about colligative properties. Anything else that's in there doesn't really matter. The questions, like, I think next comes up on the GChem site, and I just kind of skip it because I don't know that it matters, is like, it's less to do with solubility and more to do with like dissociation. So if you have something that you dissolve in water that partially dissociates, which is what the next chapter is about. So when we talk about something like sodium chloride, it just goes to this. But if I talk about something like let's say hydrofluoric acid, it doesn't completely dissociate. So you don't, so here you end up with one of these and one of these, so you get this total of 2 molar. With HF, you don't actually end up with 1 and 1. You end up with like some percentage of that. And so the Van Hoff factor ends up being a fraction. And I think they talk about that on the GChem website. We're not going to get into that because it doesn't really matter. We're going to beat that to death in the Equilibrium chapter. So just don't, if you see that, just skip over it.
Okay, thanks.
Mm-hmm. But ultimately, no matter what, like your fundamental guiding principle for colligative properties is how much stuff is dissolved. You know, that's all you really care about. Anything else that like how much, what's the total like number of moles of dissolved stuff? That's all that matters. That's sort of our guiding principle. So if it doesn't go in a solution, it doesn't affect the colligative properties. And then how the Van Hoff factor works is just dependent on how it dissociates. Yeah, so problem 29, let's see. Complete dissociation. Yes, you even say complete dissociation to make it clear. Where's the boiling point elevation? Yeah, I should work one of these out in normal class time. So if you just want to wait until Friday, I'll probably start with something like that. There's ways to make these problems a little bit more complicated by asking about like molecular masses and stuff. But I think we'll probably stick to something basic like this. But ultimately, for these types of problems, all you're doing is you're plugging things into that equation I wrote out earlier, which is that delta T is equal to I times the molality times K. What do we use? K. I guess it's called KB for boiling point. And so yeah, you got to be careful with I. I mean, we can work it. I can work it again in class. And you got to be careful that you're using molality, which is grams per kilogram. KB is just useful for figuring out what your 0.51 per molal is just useful for figuring out what units and stuff to use. So it is almost it's very plugging numbers in. So yeah, so let me start with something. I don't know if I'll do this exact problem, but let me start class on Friday with working out at least one or two of the quantitative colligative property ones. 38 and 39, let's take a look at those. Lattice energy. I'm trying to remember exactly what the equation is here. So we're looking at, so yeah, 38 and 39 are using a delta H equation. So we're looking at the delta H of solution. I just want to make sure I get the terminology right. These are pretty easy to solve. I doubt I'll solve one of these in class. And the Wikipedia articles are always way crazier than I want them to be. Like I look at that, I'm like looking for like the most basic enthalpy of solution equation on the planet, and I open that up, and it's like, yeah, like partial differential equations and stuff on there. There we go, enthalpy of solution. Yeah, okay. I get confused with like, I just forget the terms. So what you want to use for these, for 38, 38 and 39 is this equation that is the delta H of solution is equal to delta H lattice energy plus the delta H of solvation. And then if you look at problems 38 and 39, it's really just a matter of, well, I guess we talk about the enthalpy of hydration. So delta H of solvation and delta H of hydration, these are the same thing. So hydration is when you're in water. Solvation would be like, you're not in water. That's the only reason those terms are different. But yeah, what you can see once you're having to solve these, how straightforward the calculations are. So yeah, for example, in number 38, it says, okay, my enthalpy of hydration, which we just said is this. They give us a number for it. It's negative 5,247 kilojoules per mole. And then for the enthalpy of solution, they give us another number, minus 27 kilojoules per mole. And then it asks us to calculate out the lattice energy. So you just solve for that. So, you know, we can plug this in, but yeah, so delta H of lattice energy would equal whatever the delta H of solution is, minus the delta H of solvation, which they're calling hydration in this problem. And you just end up with some number. I don't know if we have a formula sheet. There might be one in like the extra worksheets section. I think I have one from like last time I taught this course. I can always post it. I think I thought about posting it, and then I was like, well, it's open notes, so you can just look them up. But yeah, it'd be useful to kind of have them all in one place, huh? Yeah, let's talk about, I'll, if I don't remember to post it, which is possible because after I leave this, I go and hang out with my son, and then, you know, I'll forget. So I won't have time to post it immediately. Just post on Piazza and we'll get one up for you guys. Yeah, so the interesting thing for me, I guess, the interesting thing is, so the equation itself is like you just plug a bunch of stuff in and you just solve. But what are these different things? So delta H of solvation, delta H of hydration, all I was saying is they're more or less the same thing. So it's the enthalpy associated with I'm trying to think of it. I guess you could say, I think to a first approximation at least, delta H of solvation is the enthalpy associated with forming the bonds between the solute and the solvent. Don't worry about, and there's some enthalpy you pay for breaking up the solvent. So for example, if I have, you know, some pure water, so these are my hydrogen bonds, and let's say I put in some sodium chloride. So now I'm forming some dipole-dipole interactions between the sodium and the water. And also with the chloride. Remember that forming bonds and breaking bonds, that's what we're talking about when we're talking about enthalpy. So it's not all of enthalpy, but that's what we're talking about generally in chemistry. So now I have these dipole-dipole interactions here. And so in going from just pure water to this, there's a change in the enthalpy. So I'm breaking the bonds between the waters and I'm forming bonds. How does the temperature play in this? Oh yeah. Temperature is just constant. Yeah, that is correct. Thanks, Madison. But yeah, the delta H associated with this process of breaking bonds, this delta H of solvation or hydration, is the enthalpy of forming and breaking the bonds between the solvent and the solute. So I'm forming and breaking bonds. Between solvent and solute. And then the delta H lattice energy is the energy associated with having to break up a crystalline lattice of something. So that's this other component, and this has to do, I think I get into like a lot of detail in this in the, whatever my lecture video is in this, but this has to do with, I've got this and I've got these chlorides. When I break up this, breaking it up, and separating these guys from one another, that's the lattice energy. So that's delta H lattice energy. And so what you're computing when you're doing this delta H of solution is you're saying, okay, so here we had to solve for the lattice energy, which is, you know, it's part of the same thing. But when you're talking about delta H solution, you're talking about the enthalpy associated with breaking up a crystal and the enthalpy associated with and the enthalpy associated with forming and breaking bonds. So basically all you're doing whenever you're calculating, I guess, the delta H change for any kind of chemical system, you're ultimately computing all the bonds formed and all the bonds broken. And we see this, I think we do this in like general chemistry 1, where you look at like bond dissociation energies or something, and we have that equation where it's like delta H of reaction is equal to like the delta, what is it? It's like the sum of the bonds broken minus the sum of the bonds formed. I might have my signs backward there. You know this, and you look it up in a table and you sum them up, and it's like the problems aren't that hard. That's essentially what we're doing up here, but like it's just a little bit more, the way we have to get at it is a little weirder because we're not dealing with covalent bonds, but it's the equivalent of saying that. I'm saying how many bonds are broken, how many bonds are formed, and I'm just summing up all the energies for that. And that's what ultimately gives me delta H of solution. That's how all the delta H calculations work. Like what's formed, what's broken, sum them up. And how you have to get at that can be kind of weird. And that's what's happening here. Particularly the lattice energy is a strange one. Anyway, so yeah. On Friday, we'll punch through like probably one of the osmotic pressure problems or something, just so I probably should talk about the Van Hoff factor and stuff a little bit during normal class time. And then I'll hopefully get to touch on the equilibrium stuff on Friday, and then on Monday through Friday of next week, we'll just work equilibrium problems nonstop. Yep. Otherwise, thank you guys. And answer to 38, I have no idea. I'm really bad about just actually finishing out the math. Let's see. So you'd have 5247 enthalpy of hydration. Delta H of solution is what did you have? Minus 27 minus 5,247. Did I do that wrong? I don't know. Somebody else got it, so it's probably correct. Yeah, but minus 20 minus 5. Yeah, plus 5,220. That makes sense. Yeah, okay. Yeah, lattice energy should be positive. Okay. Yeah, we're good. That's right. Cool. Yeah, that's right. So yeah, so you can ask yourself, if you want to think about the question deeper, is like, what do I expect the sign change to be on the lattice energy? But again, those are deeper questions. How intensively are we going to get in that exam? I don't know, not super intense, but yeah, 39 you'd solve in almost the exact same way. Why do you expect it to be positive? Because remember that our sort of like fundamental rules for delta H is that when you form bonds, that releases energy and it's negative. And when I break bonds, it's positive. So if I have a crystal of sodium chloride, right, the lattice energy is the energy associated with breaking that crystal up into sodium and chloride in this particular case. So, I'm going in the direction of having a solid with bonds to a solution where I've broken those bonds up. And so if I'm breaking the bonds up, the lattice energy is positive. If I'm forming the crystal, so I'm now, let's say you're going in the reverse direction, then I expect them to be negative. It's just, it all comes back to forming bonds, delta H is negative, breaking bond, delta H is positive. So the lattice energy hurts you in terms of actually getting this thing in a solution. Delta H of solvation is more or less break even. Yeah, I don't know. There's a lot to think about there. Yeah, thank you. I will have a nice day with my son. I will see you guys on Friday. Anyway, it's been fun. Thank you guys for coming to office hours and asking questions.